Okay, we are now on the solutions for quiz 6. Okay, we have two masses, m1, m2. We want to compare the force of F of 1 on 2 and the magnitude of the force of 2 on 1. It's just the force of gravity. This is just Newton's third law. It's the force, or you can just say the formula for gravitation. The forces will have the same magnitude, opposite directions. Okay, they have the same size. Now, near the surface of the Earth, the acceleration due to gravity is 9.8. The radius of the Earth is 6,370 kilograms. How far from the Earth's center do you have to go to reduce g to a value of 2.7 meters per second squared? Okay. All right. So the point is they don't give you a whole lot of information here. So it's a small g is going to be Fg divided by m, so just the force of gravity divided by small m. So the formula is capital G is capital G times capital M times m over r squared divided by m. So the formula for small g is capital G times m capital M over r squared, where capital M is the mass of the Earth. Okay, so now at the surface, we know that capital G times capital M over r e squared is equal to 9.8. But for the new case, we're going to have capital G times capital M over r squared. That needs to be 2.7. So the idea is I'm just going to simply figure out how much bigger r must be compared to re. So as something times re. So I'm going to take the ratio of g surface to g nu. This will give me 9.8 over 2.7. But if I look at these formulas, the ratio will give me r squared over re squared. Okay, so that gives 3.63. And so r squared is equal to 3.63 re. So r is equal to the square root of 3.63 re. And we get 1.21 times 10 to the 4th kilometers. If you found this a little bit of a complicated way of figuring it out, you could have done a more straightforward method. You could have calculated what you need to calculate. You could extract the mass of the Earth from the formula, and then you could have gone straightforwardly and figured out what r needs to be. It would take a little bit longer, but it would maybe conceptually a little bit simpler to follow that way. Okay, next problem. Let's find the speed of a satellite in a circular orbit around the center, around the Earth with a radius of 2.15 times the mean radius of the Earth. Okay, so just v orbit is equal to square root of g times capital M over r. Plug in g is 6.67 times 10 to the negative 11. M is 5.98 times 10 to the 24. And then we're told that the radius, this r is 2.15 times the radius of the Earth, so 2.15 times 6.37 times 10 to the third. But there's another 10 to the third because it's kilometers. And so we have we end up with 5.397 times 10 to the third meters per second. Next problem. A rock is dropped from outer space, the initial velocity 0, at a distance 1.7 times the radius of Earth from the Earth's center. What speed will it have when it reaches the surface of the planet? Ignore air resistance. They give you the parameters R Earth, M Earth. Okay. So this is conservation of energy. Kinetic, it will be K initial plus U initial is equal to K final plus U final. Initial kinetic energy is 0 because it starts from rest. Initial potential energy is minus G times capital M times small m over 1.7 RE. That's where it starts from. Then the final kinetic energy is 1/2 mv final squared. We're trying to figure out what V final is. And the final potential energy is minus capital G times capital M times m over RE. Okay, so let's do some simplification here. Let's get V final squared, divide by m times multiply by 2. Bring these guys together. Okay, G capital M times small m, they both have those. We have an RE in both of those. But the second one has a 1.7 in the denominator. So I can pull out some factors out here to try to make it so I don't have to punch in so much stuff into my calculator. and then I 1 minus 1 over 1.7. You see I'm just factoring out a factor Gn over Re here. The G is also there. This ends up being equal to, this inside the parentheses, or the brackets is 0.412. So we get 2 times 6.67, that's negative 11, times the mass of the Earth. This was 5.98 times 10 to the 24, divided by the radius of the Earth, which is 6.38 times 10 to the 6, times 0.412. That comes up to 5.15 times 10 to the 7. Take the square root, and get 7,177 meters per second. Okay, now an automobile with mass 1,300 newtons is observed to bounce up and down after hitting a pothole with a period of 1.05 seconds. Okay, so if each shock absorber is acting like a spring, find the effective spring constant for a single shock absorber. So there are now 4 springs acting together. Since they make the total spring force 4 times as big for the same displacement, x. Okay, you displace all of them by the same amount x, you get 4 times the force. So therefore, the spring constant for all the springs together is 4 times the spring constant for the single one. So let's call this K all for clarity. K all. So the period is 1.05 seconds, but that's also equal to 2 pi divided by the square root of m over K all. And so I can now try to solve for K all. I have 1.05 divided by 2 pi, so the square root of m over K all, square both sides, and then K all is equal to m divided by 1.05 over 2 pi quantity squared, and I get m is equal to 1,300 divided by 1.05 divided by 2 pi quantity squared, and I get 4.65 times 10 to the 4th meters. Now for the spring constant of one spring, that's 1/4 of the spring constant for all of them, that comes to 1.16 times 10 to the 4th newtons per meter. Now the graph shows the x displacement as a function of time for a particular object undergoing simple harmonic motion. So this is the time here. So it's going to be described by xt is equal to a cosine omega t plus 5. Okay, and they want to know the amplitude of the oscillation, so how big this oscillation is. Right. So we can look at it. It goes up to 1.7 or so, and it goes down to negative 1.7. So the amplitude is 1.7. Okay, the period is the time interval between 2 successive repetitions of the wave. So we'll take this point here up to here. So this is 0. This is about 5 point. It's less than 5.5, so it's about 5.2 or so, and that's what the period is, 5.2. Okay, the mass, a mass of 0.8 kilograms is hanging from a spring with a spring constant of 3 newtons per meter. At a distance of 0.2 below the equilibrium, it has a velocity of 0.8 meters per second in the downward direction. What is the amplitude of the oscillation? So the mechanical energy, the total mechanical energy is 1/2 kA squared. That's the sum of the kinetic energy plus the potential energy. That's 1/2 mv squared plus 1/2 kx squared. So let's plug in the values. 1/2 0.8 is the mass times 0.8 also for the velocity squared, plus 1/2 3 is the spring constant times 0.2 squared for the displacement. So this comes out to 0.316 joules. So 1/2 kA squared is equal to 0.316 joules. So now we know the spring constant is 3, and so we can solve for a squared is equal to 0.316 times 2 to get rid of the 1/2 here, divided by the spring constant, which is 3. That comes out to 0.211, so the amplitude is 0.46 meters by taking the square root. Number 9. An object is performing some harmonic motion with an amplitude of 26.1 centimeters and a period of 2.85 seconds. Determine the maximum speed of the object. The maximum speed is a times omega, so we need to know what omega is and what a is. Okay, a is just given as 26.1 or 0.26 meters. You get omega, so the period is 2 pi over omega, so omega is equal to 2 pi over the period. So 2 pi over 2.85, that's 2.20 radians per second, so 2.20 here, and multiplied together, that gives 0.575 meters per second. Next one, the last one, a small but heavy lead weight is attached to a lightweight string with a length of 0.75 meters. Determine the natural period of the lead weight if it oscillates with a small amplitude on the end of the string. Okay, the period is 2 pi times the square root of L over G. The 2 pi over L is 0.75, G is 9.8, so that comes out to 1.74 seconds.